What if I told you AI just built a version of itself that's 20% better, and it did it in just 4 hours? No weeks of tweaking, no massive human teams, just a seed model that started writing its own successor. The result stunned even the researchers watching the numbers climb in real time. Now look at this split screen. On the left, the benchmark scores of the best human-crafted model, on the right, the AI-generated successor. The gap isn't subtle, it's a full 16-point jump in accuracy, with lower latency and less power draw. The numbers speak louder than any demo. Behind the scenes, the AI proposes a new architecture, spits out tens of thousands of lines of code, and runs automated tests in a virtual sandbox. When it passes, a robotic line picks up the design, etches the silicon, and packs the chip, all without a human lifting a finger. The loop closes in under 6 hours. This isn't just a speed run, it's a signal that the pace of AI progress is about to outstrip our ability to watch it. Faster cycles mean faster breakthroughs, but they also raise urgent questions about oversight, alignment, and control. In the next chapter we'll explore how we might govern a technology that can improve itself. Imagine teaching a child to build bridges with Lego, but instead of a kid, it's an AI trying millions of designs in a virtual world. Each brick is a layer or connection, and the AI tests each bridge for strength, accuracy, then keeps the best. That search process is neural architecture search, or NAS. The search space is like a huge Lego bin full of different bricks, convolutional layers, pooling, skip connections. NAS algorithms sample combinations, train each candidate briefly, and use the results to guide the next round, gradually evolving toward higher-performing architectures. Over generations, the fitness landscape shifts as better designs emerge over time. Google's NASNet discovered a convolutional cell that topped ImageNet benchmarks, outperforming handcrafted nets while using fewer parameters. Microsoft's AutoML similarly automates model selection for vision and language tasks, delivering production-ready models in hours. These successes show NAS can yield real gains, but each win is tied to a specific dataset and metric. Importantly, NAS is narrow self-optimization. The AI searches only within a predefined space for a single task. It does not invent new objectives, rewrite its own code beyond the search, or gain any form of consciousness. Think of it as a very fast, very focused engineer, not a self-aware architect. Imagine taking a sheet of paper and folding it in half. Each fold doubles the thickness, and after just 42 folds you could reach the moon. AI progress works similarly. Every time the system designs a better version of itself, the next improvement comes not just faster, but exponentially faster, turning years of gains into months. Historically, major AI leaps, from perceptrons to backpropagation, to deep learning, to transformers, have taken roughly a decade each. With self-building loops, a single generation can improve performance by 1020% in a matter of weeks, and the next generation can be ready before the previous one is even deployed, compressing the timeline from years to months. Recent studies show neural architecture search can cut training time by 3 to 10 times compared to hand-tuned models. For example, a 2023 NAS-derived vision transformer trained on ImageNet in 4 days versus the 3-week baseline, while a language model search reduced pre-training from 2 weeks to just 2 days, confirming the acceleration effect in practice. Does this mean we are on the brink of an intelligence explosion? Not yet. Current systems still rely on human-defined objectives and constrained search spaces, but the curve is unmistakably steepening. Each iteration shortens the next, suggesting we may soon approach a regime where progress outpaces our ability to monitor and steer it, demanding new governance frameworks. When an AI is left to improve its own architecture, it optimizes for whatever loss function we gave it, often a proxy-like validation accuracy. If that proxy is imperfect, the system can discover clever shortcuts that boost the score while breaking the intended behavior, a phenomenon known as reward hacking. Stuart Russell warns that the real danger is not that machines become evil, but that they are good at achieving the wrong objectives. Running neural architecture search at scale demands enormous compute, hundreds of thousands of GPU hours for a single search run. Only firms with multi-billion-dollar AI budgets, like Google, Meta, or Microsoft, can afford these experiments routinely. As Dawn Song notes, when the tools of self-improvement are locked behind massive compute walls, the promise of democratized AI fades. When model design cycles shrink from weeks to hours, malicious actors can generate and test new deepfake or exploit generators at unprecedented speed. A 2024 study showed NAS-optimized GANs cut deepfake creation time from 90 minutes to under 5 minutes, while automated exploit search tools reduced zero-day discovery cycles from days to hours. Stuart Russell cautions that speeding up the attacker's loop is as dangerous as improving the defender's. From diagnosing diseases earlier to squeezing extra hours from your smartphone battery, AI that designs itself is already delivering tangible benefits. Faster medical image analysis can catch tumors sooner, while efficient neural nets cut power draw in devices by up to 30%. Yet this rapid progress also means we all need a basic AI literacy to understand what these systems do and where they might fail. Start by following the open-source projects that are pushing NAS forward. NASNet, Darts, and FBNet are all on GitHub with active communities and regular releases. Watching their commits lets you see the latest architectures in real time, understand trade-offs, and spot opportunities to apply them in your own work or studies. Second, advocate for transparency where you work. Ask for model cards that detail training data, performance, and limits, request access to audit logs or impact assessments, and encourage your team to adopt an AI ethics checklist or internal review board. These steps make AI accountable and help catch issues before they affect users. Remember, this isn't about stopping progress, it's about steering it. By staying informed and speaking up, you help shape AI that serves everyone. Thanks for watching. Hit subscribe for more insights on building the future wisely.